conservation of momentum. Now it is conservation of momentum in one dimension that I'm going to derive and talk about in this video, although I will mention how you can tackle momentum in 2 dimensions and even 3 dimensions, which you're going to have to break down into its vector components. So when you are beginning and studying the conservation of momentum, you can think about the conservation of energy. So you know that when you're talking about the conservation of energy, you have the total energy which is coming in is always equal to the total energy which is coming out in a closed system, assuming that there's no other energies externally that is being seeping into that system. Well, the same thing happens with momentum. Now, once you understand what momentum is, which is nothing else but simply mass multiplied by the velocity of an object, and you also understand impulse, and impulse is the change in momentum, or simply what the force in terms of the application of that force would be, multiplied by the change in time. And I can put up a link up above there, okay, if you want to review on that concept of momentum and impulse, because you're going to need it here. So the first thing that we'll do is just talk about a couple of key definitions. And these key definitions are going to take and shape how momentum goes about, especially when you're going to start be doing some examples. And we'll talk about both of these in future videos as well. So collision is nothing else when you have an event where 2 or possibly more objects come into contact and exchange momentum and possibly even energy. So within here, that collision, okay, is that we're going to be considering here is going to be for 2 objects, but of course you can extend it to multiple objects as well. So now with that explosion, so there's a little bit different than a collision. So in an explosion, an event is occurring where just one object starts to break apart into multiple pieces with the momentum being conserved, and then energy is being rapidly also released. Now, in terms of its collisions, so what I have here on the screen, we'll imagine that we have just 2 objects right here. And we are going to be doing this in 1 dimension. So now if you have these 2 objects and they have a certain amount of speed or velocities, well, then they have momentum. Now, if there's going to be a collision between these 2, we can show that momentum, the conservation of momentum, means the following. So notice that right here, what we have, it is your initial momentum of the first mass, and it is added to the initial momentum of the second mass. So before the collision happens, and just right after the collision occurs, it turns out that the momentums of the final, which means after the collision, when you add them together, are going to be equal to the summation of the initial momentum. So meaning, okay, initial momentum is going to be equal to the final momentum. The same thing as you see in the conservation of energy. So let's try to derive exactly where this comes from. So if you take these, and they're going to be coming into a collision course, so, I'll bring them together, and let's say that they're colliding right there, then because they have a certain amount of speed, so they have a certain amount of energy, they're going to collide and they're going to be exerting forces on each other, and they're going to be kind of bouncing off depending on what their sizes are, and they're going to be changing their possible speeds in here. All right, so that might certainly happen. So let's try to draw out kind of the important items here. Now, and I do want you to recall, so Newton's 3rd law, which is for every action, you have an equal and opposite reaction, which means that whatever force is going to be applied by one object on the other, okay, there's going to be an equal and opposite, okay, which is going to be applied on that first one. So in short, so we know that when you have this, so let's imagine that you have a force, okay, and that force from object number 1 on object number 2, okay, so this is the force that you would have, would be equivalent, or simply you can write it out as the force of the object number 2 applying on object number 1. So both of these are going to be equal to 0, meaning that if you're going to be transferring this back in, so what you're going to have is the following. So you're going to have this particular equation, okay, holding, and this is nothing else but Newton's third law. So that's what has to hold by Newton's third law. So now, if we have this, then we can start to expand this out. Now, let's go back and think about impulse, okay, and then the changes in momentum overall. So what do we know about impulse and then how impulse was defined? Now, I'm going to come back to this particular equation, so we'll hold it there momentarily for us. And now let's think about impulse in total, okay, so that we can derive that conservation of energy. So if you're thinking back in terms of impulse, so what you would have is the following. You know that you would have the force, and this would have been for a certain amount of time. What is the impulse change of this? That means that we're going to be applying this particular force right there. So that's the force coming from object number 2 on object number 1. And this is equal to the change in momentum, okay, of that first object. And now, of course, the change in momentum, so if you would be writing this out, so that would have been the actual change in momentum that we would have for that first object. Now, I can take the same thing, so I'm going to borrow this so I don't have to rewrite it again. And if I now duplicate this right here, I will change the color so that it pops out for us, okay, and there's a distinguishing feature. Now, if you were doing the actual impulse change for mass number 2, then what would have happened in here, so this would have been, instead of the force from 2 on 1, this would have been simply the force on, okay, coming from 1 on 2, right there. And then this right here, this is just the change in momentum of that second object. So I'm going to be just deleting all of these. And there we have our 2 changes in momentum. So now, if I go back to what I said, which is this right here, so if I now take this overall, notice that what I can do is I can multiply both sides, so within here. So if I take Newton's third law and I can multiply both sides, so I'm going to leave it a little bit of space here, and that multiplication would have been by the change in time right there. So if I do this, it's still obviously equal, but notice that this right here, well, that's just the change of the momentum of that second mass. And that particular change, well, we have that right here. So I'm going to duplicate that in. I can put it in right there. So that's going to be on that side. And then this is equal to now, and notice that this right here, except it's negative. So I'm going to put this in brackets in here. That would have been this right here. So if I now take that over, I'll duplicate it in, I'll put it in right there. So this is what we would have. Now, if you factor in or distribute the negative, all right, and then you start to change over and you switch the sides, you do the algebra, you'll notice that you will get your conservation of momentum right here back, all right? So let me just do that. And so there you have it, all right? So as you kind of change these things over, okay, so this is exactly what you're going to be running into, and that's your conservation of momentum. So notice this is momentum of your fund. So this is on the left-hand side, I have the final. That's the momentum final of object number 2 plus the momentum of object number 1. So when you're adding them together, they're just equal to the summation of what the initial momentums were. So hence, we have a conservation of momentum overall. And that is the equation that you would have. Now, it doesn't matter if this is on the left or on the right, okay? So initial or final, that's up to you, depending on how your teachers are setting this up. But that's what you would have over here. Now, how can we possibly use this change of momentum? So this equation, it's not difficult for us to do, okay, in an example. So here's an example. So it's a simpler example just to get ourselves started. So notice that we have a 60 kilogram person stands on a 5 kilogram skateboard at rest. So they're not moving. And then, okay, that person is pushing off the board and then jumps forward at 2 meters per second. What is the skateboard's recoil velocity? So what is that velocity right there? So notice if you're going to be taking in your equation right there, so we can, I'm going to just highlight, okay, so person, okay, and skateboard. So that's what we have. Notice that they are at rest. So what does that tell us? Well, that means that at rest, this initial amounts, okay, so we could certainly substitute all of these in, but if they're at rest, then the speeds are 0. Now, if they were not at rest, you know, you can certainly put in the speeds if you wanted to. But in this case, both of these are going to be canceling each other off. They're going to be 0 because the speeds are 0. And now notice that the board, okay, so the person as they jump off, the speed is 2 meters per second, and then we want to know what the skateboard's, okay, recoil is. So it doesn't really matter which one you name as M1 or mass 1 and which one is M2. That's completely up to you. But if you substitute this back in, so we know that this is 2 meters per second, okay, so plus this is going to be 5, and then your final speed. And this final speed is going to be the final speed of the skateboard. So now notice this can switch over on the other side. So you're going to get this. 2 times 60 is 120 right there. And then 120 divided by 5, which is going to be, so right here, VF. So we can take that in. So 120 divided by 5, which is 24 meters per second. Okay, now we have to be careful here because this is negative. Okay, so that's going to be now negative. And the only thing that the negative means is that it is in the opposite direction, right? So the speed is in the opposite direction of the person. So the person's going in one way and then the actual skateboard's going in the other. So we're using, okay, the conservation of momentum in order to find that information. And that's where this equation is super useful to be able to use. All right, so that's that equation. Now, I mentioned at the beginning, okay, so that if you do have these things happening, notice that we're only talking about in one dimension. Now, if you're going to start to continue with physics, you know, it might so happen that it's not just in one dimension, you know, going back and forth, left and right, or up and down, etc. But it might be in multiple. So if you're starting to have angles, then you're gonna have to break things down into components, but the actual summations do not change. Okay, so notice that if you do have multiple objects, okay, so right here, so the sign is just a summation, meaning adding all of these up. So this and this, okay, so this is initial and final. That's exactly what we have in here. The only thing that we're saying now is that this is both in the X component, in the Y component, and then possibly in the Z component or Z component. So that's what this right here, okay, is exemplifying. So you would have to break this thing down, and then momentum would still be conserved overall. All right, and this is definitely essential when you are dealing with collisions, okay, between objects that are at an angle, all right, or explosions that send off things in various directions. So you would have to be able to do that, okay, overall. All right, so that's the introduction to the conservation of momentum. So it goes hand in hand with the conservation of energy. We do have a very nice equation in one dimensions. If you continue on, you can, by the way, you can certainly have more than just 2 objects, but normally when you're beginning this in your studies, that's what you'll have. You'll start, and please understand first 2 objects so you can expand it onto other objects if necessary. All right, so there it is. That's the derivation. I will also add a full out summary, okay, so I'll do a little bit of a summary, okay, and I'll provide the document in the description. Thanks for watching. We'll see you in a future video. Bye, everybody.